Alright, what's up, guys? I'm going to show you how to make the graphs for your Tensile lab. So, in the lab, I showed you how to collect your data. So, you'll have an Excel for each metal. You'll have your aluminum, you'll have your brass, 1018, so on and so forth. And so, the data we collected was the stress and the strain. And so, from that, can kind of copy and paste all the data into one Excel so that we can make a stress strain curve with all the metals on one graph, right? So we're going to want to insert a chart and we're going to do a scatter plot with the smooth lines, right? And so right now it's a blank graph. So right click that, or you can click over here, select data, and we want to add an entry. So let's say first we'll grab aluminum, the X values, you want the strain. So copy, scroll down. Okay, and then for the Y values, you want that to be the stress. Just watch out with this uh thing there, and then you'll highlight the stress. Oops, and done. If I say OK, you'll see it's added to the plot. And so on the plot, we're gonna want axis titles for our X and Y. We're gonna want a legend because we're plotting multiple data sets, like multiple things, and then a chart title. So your chart title can be like tensile tests of metals or stress strain curve of metals, whatever you want to name it. And then on the X, we have the strain. Make sure you have your units. Even though it is unitless, we'll just write inch per inch. If you want, you can transform your data. You can multiply all the strain values by 100, and then you can have on the x-axis strain percent if that's what you want to do, which is totally fine. And then on the y, we'll have the stress. Units are PSI. Right, so right now we just have aluminum. So I'll click on the graph again, right click, select data, and we want to add another entry. So let's add brass. And then it's the same thing as before. And then you click OK, done. Then we'll add another one. So we'll do 1018, X values, and the Y. And we'll click OK. I want to add our final one, the 4140. And as you see, it's already being added to the graph. Looks weird right now. Not sure why, but the data, there it is. The data will be fine. And so we're gonna add 4140, X, and Y. So we have our four metals, click OK. And now we look in the chart and you see all four metals are there. And so from here, it's much easier to compare the metals and make conclusions. Also, let's say you want to change the color, like for here in the lab, brass was like a yellowish color. So if you want to change it, you can change its fill and outline to make it yellow. And then aluminum was like a white kind of color, so not sure how you could replicate that. It's kind of like an off-white, so maybe something like that. And then 1018, um, a low carbon, so maybe like a gray or something. And then the 4140 is high carbon, so black, something like that. If you want red or, whatever you find to be the best choice, whatever you want. But anyway, you see the steels are much stronger. They have a much higher yield strength and UTS than brass and aluminum. And so we remember the steels are BCC crystal structure, while aluminum and brass are the FCC crystal structures. And so looking at this, we can say, well, the BCCs are stronger, while the FCCs are more ductile. And so that's, a conclusion to make. And a reason for this is that the FCCs are more closely packed. And so it turns out it takes less stress to induce slip, which is the mechanism for plastic deformation. So them being closely packed makes them more ductile. And then the BCCs, because they oppose plastic deformation more, they become stronger, right? So that's comparing the two different crystal structures. And then if you look at the two steels, you see 4140 much stronger than 1018, right? The addition of carbon and the alloying elements um, make it stronger. However, adding stuff like that, you tend to see a drop in ductility because you're increasing strength. So 1018 more ductile, but much less strong. However, steel in general is much stronger than aluminum and brass. So that's why you see it in structural applications. It's cheap, it's strong, but it's also ductile. So steel is really good. But yeah, anyway, this is just about everything your memo asks of you. You can just come in here and label the yield and UTS points, strain to failure. You can put the reduction of area values, the modulus values, and then doing the toughness fracture energy calculation. You can put that here somewhere. Um, but yeah, I think you can just save it to a new sheet or something. Uh, okay, yeah, there you go. If you want this to be bigger, and then you can print it as a PDF, and it's much easier to draw on it and annotate. But yeah, that's just showing y'all how to make the tensile graph. All right, that'll wrap up the video.